So welcome to this new video. Last class we were discussing about iron carbon phase diagrams, and now let us look into failure and what are the different failure mechanisms and all. So failure of a material component is the loss of ability to function normally or to perform the intended job. So failure is always an undesirable event for several reasons, which I like. It puts human lives at risk, and we have some economic losses, and we will be having interference in the product and the services. So failure can lead to these different types of events. So generally there are three ways of failure. The first is excessive elastic deformation. So failure due to excessive elastic deformation, example, it is buckling. So buckling is caused due to excessive elastic deformation, and it is controlled by design and elastic modulus of the material. So in the second method or second way for failure is due to excessive plastic deformation. So due to relatively high plastic deformation controlled by the yield strength of the material, so creep, stress rupture or loss of shape, these all failures, these are a result of excessive plastic deformation, and these failures will take place at a relatively very high temperatures. So these failures are occurred at high elevated temperatures. So another method of failure is fracture. So the fracture, it involves complete disruption of continuity of a component. So fracture, which is a fundamental type of failure, it can cause under static load. We can say we will have a brittle or a ductile fracture. So when a static load is applied on the material, it can lead to a brittle fracture or the ductile fracture based on the type of material. So under fluctuating or a cyclic load, the loads are periodic load is applied on the material, we will be experiencing a fatigue. So fatigue is the failure in which the most machine parts will fail in service. Okay, first let us look at a fracture. So fracture, as I said, is a fundamental type of a failure. So when load is applied on the body will separate into two or more pieces. Okay, so fracture is a separation of an object or material into two or more pieces under the action of stress. Okay, so the fracture of a solid usually occurs due to the development of certain displacement discontinuity surfaces within the solid. So it is caused due to certain discontinuous surfaces present in the material. Okay, the fracture is classified based on the several characteristics features. So there are generally two modes of fracture. There is ductile fracture and brittle fracture. So ductile fracture is caused by crystallographic mode is shear, and in a brittle fracture the mode is cleavage. And the appearance of the separated parts or pieces will be fibrous and grey, and in brittle material it will be granular and bright, and the appearance will be bright and the granular. The failure will be taking place inside the grains. And in ductile material, the crack propagation is along the grain boundaries, and in brittle material, the crack propagation is through grains. Okay, so let's look at fracture modes. So as I said, there are two modes, ductile fracture and brittle fracture. So these two are related terms. You can generalize the fractures it will be based on these three modes. First mode is a rupture, then a cup and cone, and brittle. So based on the material and application of load, these three modes or these three modes of fracture will be taking place. So first one, you can see here is an example of a pure metal, or we can say a soft metal, for example a gold or a lead, pure gold material. So these soft materials, when load is applied, here we can see that the specimen necking will be taking place. So here we can see the specimen next out to a particular point, and we can see two pointed surfaces on the two separated parts. So here we have seen a highly ductile fracture, or we can say it's a rupture. So the high ductile fracture has happened in this case. But in the second case, when the load is applied, we can also see a necking, and it is due to a moderate ductile fracture. So here there is a moderate ductile fracture. So it is due to the moderate amount of necking. And also this fracture is also known as a cup and cone fracture, because the separated parts, the one part will be in the shape of a cup and the other part will be in the shape of a cone. Okay, so this is an example of a moderately brittle ductile fracture. So the third one you can see here is an example for a brittle fracture. So in brittle fracture, the fracture will take place without any plastic deformation. That is, here we cannot see any necking or any elongation. So it will be a catastrophic process. The failure will be unpredicted, and there will not be any warning. There will be there will not be any plastic deformation, or a very little plastic deformation. Now let us look into these stages in cup and cone fracture. So cup and cone fracture is due to the moderate ductile fracture, and these are the three different stages. So the fracture having this characteristic surface contour is termed as a cup and cone fracture, because one of the meeting surfaces is in the form of a cup and the other like a cone. As I said earlier, the meeting surfaces will be in one meeting surface will be in the shape of a cup and the other will be in the shape of a cone. Okay, these are the stages. In the first stage, there is an initial necking, or a neck formation will be taking place due to the tensile load application. And in the second stage, you can see here there are small micro voids will be formed. So small cavities or micro voids will be formed due to the application of load, and these formed micro voids can be will be occurring in the central region, and we can observe it under the microscopes. And in the next stage, these micro voids they will coalesce together and will become sufficiently large and forms a crack. So the crack will be propagated in the third stage. So finally, in the fourth stage, a shear will be taking place, and this shear force will be will approximate at a maximum of 45 degree to the tensile load axis. So the angle of this shear will be 45 degree to the application of the tensile load. And in the final stage, we have seen that after shear happening, the surface will be separated, and we will be having an appearance of a cup and a cone. So here is a cup and here is a cone. So and we can identify the two regions. This central region is known as a fibrous region, and this region along the boundary is known as the shear region. So here we will be having shear region. Okay, in this figure we can consider an example of aluminium and mild steel. So aluminium will be the material which will be undergoing a ductile fracture. So the separated mating parts will be in the shape of a cup and a cone. Okay, but in the case of mild steel, it will undergo a brittle fracture, and the surfaces will be looking like this, because in the crack is generated almost perpendicular to the tensile load. So here the crack, we can see the shear region will be 45 degree to the tensile load, but in the brittle fracture you can see that the crack is almost perpendicular to the direction of load. So the crack propagated, you can say it is perpendicular to the direction of the load. Now let us see the difference between ductile fracture and brittle fracture. So ductile fracture, it requires a high strain energy, but the brittle fracture will be requiring very low or a lower strain energy compared to ductile fracture. And the stress in ductile fracture, it will keep on increasing when the load with the deformation taking place. The stress will keep on increasing, but in brittle fracture the stress will be a constant, will remain constant. Okay, and the crack propagation is slow in ductile fracture, but it will be very fast, and without any warning the process, the crack propagation will be fast in brittle fracture. So in ductile fracture we have plastic deformation, so we will be having a warning. We can observe a plastic deformation in ductile fracture, but there will not be any warning or any signal in brittle fracture. So it will be a catastrophic failure or catastrophic process in brittle fracture. And the deformation is extensive for ductile fracture, and it will be very little in brittle fracture. So due to plastic deformation, we can observe a necking in ductile fracture, and there will not be any necking in brittle fracture. And the fracture surface will be rough and dull, but in brittle fracture the fracture surface will be smooth and bright. And for example of materials for ductile fracture is most of the metals which are not too cold, and in brittle fracture, as you know, the examples are ceramics, glass, ice, and these are brittle materials which undergoes the brittle fracture. So now let us look deep into ductile fracture. So ductile fracture in tension occurs after appreciable plastic deformation. So ductile fracture before failure, it absorbs a lot of energy. So a lot of energy is absorbed before failure. So it is usually preceded by necking. So as I said earlier, we can observe a necking in the initial stage. Okay, it exhibits three stages. The first stage is the formation of cavities, then the growth of cavities, and the final failure involving rapid crack propagation at about 45 degree to tensile axis. So as I said earlier, first we will be having a formation of microvoids or small cavities, and these cavities enlarges to form cracks, and these cracks propagation finally separates the material into two pieces, and the crack propagation will be 45 degree to the tensile axis. Okay, thus for fractography of ductile fracture reveals numerous spherical dimples separated by thin walls of the fracture surface. So fractography is a study of fracture surface of metals. So fracture surface of metals are studied, and it is observed that there are numerous spherical dimples separated by thin walls on the fracture surface in the case of ductile fracture. So this is the forces: the initial necking, the cavity formation, and so the microvoid formation, and forming a large cavity or a crack, and finally shearing the material into two pieces. So So these are the stages in ductile fracture. So next is brittle fracture. So the brittle fracture takes place with a little or no preceding plastic deformation. As we discussed earlier, there will not be any warning or any signal before brittle fracture. We cannot see any plastic deformation, or we will be having a very little or minute plastic deformation in certain material. So it's a sudden process. So it occurs often at an unpredictable levels of stress by rapid crack propagation. So we cannot predict the material. If not studied about it, we cannot predict when the material is going to break or crack. So it will be at unpredictable levels of stress. There we can observe a rapid crack propagation, and the crack propagated will be nearly perpendicular to the direction of the applied stress, and hence it is called a cleavage fracture. Since the crack observed is perpendicular to the application of the tensile load, it is also known as the cleavage fracture. So most often the brittle fracture occurs through grains, so that is transgranular. So the fracture here, it will be passing through the grains. Okay, so and also in the case of brittle fracture, the amount of energy absorbed will be very less, and thus it will be leading to a rapid crack propagation. And also this crack propagation is unstable, and we cannot restore. There will not be any restoring force to slow down the process or slow down the crack, and the crack will be propagated in no time. Also in this brittle fracture, there is a successive breaking of bonds, and it will continue to break atomic bonds, and it will break rupture, and these bonds keeps on breaking, and finally the brittle fracture will be taking place. So the three stages of brittle fracture is: first is plastic deformation that causes dislocation, pile-ups at obstacles, and next is micro crack nucleation as a result of build-up of shear stresses, and third is eventual crack propagation under applied stress aided by stored elastic energy. Okay, that's about ductile fracture. So next is stress racers, or the stress concentration, what we know. So stress racers are sharp corners, grooves, notches, or acute changes of section that cause stress concentration under normal loadings. So in a material, the sharp corners, grooves, or notches, or changes of section, so these all are regions where the stress will be concentrated when load is applied. So in this example, you can see we here an abrupt change in the stress flow lines you can observe. So this abrupt change causes high stress concentration in this transition zone. When the section transitions from one zone to another, due to the abrupt change in the stress flow lines, the stress concentration will be higher, and the material will be having a high concentration stress area over here. If the transition is smooth, we can say that we will be having a lower stress concentration. So they can be found on both rotating. The stress concentration can be found both on rotating and static components. The stress concentration, also known as stress racer or stress riser, is a location in an object where the stress is significantly greater than the surrounding region. So in this location, the stress will be higher than the other regions. Okay, so the stress concentration occur when there are irregularities in the geometry or material of a structure component that cause an interruption to flow of stresses. If the flow of stress is interrupted by the geometry or the structural component of the material, the stress will be concentrated. So here in this figure, you can see this is the region of stress concentration. So when load, this is a biomaterial, an implant, and we try to find the stress concentration area. So when the load is applied over over here, and this region will be the stress concentration region, and the maximum stress will be observed in this region. So next is primary and secondary stress. So primary stress is related to mechanical loading directly and satisfies force and moment equilibrium. And secondary stresses are those arising from geometric discontinuities or stress concentrations. Stress concentration. So fracture toughness is a property that is a measure of material's resistance to brittle fracture when a crack is present. Okay, so here you can see in this figure the stress profile across a cross section containing an internal crack. So as you can see in this profile, the magnitude of the localized stress will be reduced or diminishes with the distance away from this crack tip. Okay, here sigma 0 is the nominal stress, and the applied load is divided by the specimen across this cross-sectional area. Okay, so if we assume that the crack has an elliptical shape and is oriented perpendicular to the applied stress, so if we assume that this crack generated as an elliptical shape and is oriented perpendicular to the applied stress, then we can say the maximum stress at the crack tip sigma m is equal to 2 sigma 0 into A by rho t the whole raised to 1 by 2. So where sigma 0 is the magnitude of the nominal applied tensile stress, which is shown in this figure. This is sigma 0, the nominal stress applied, and rho t is the radius of curvature of the crack tip. So the radius of curvature of this crack tip is a rho t, and A represents the length of a surface crack or half the length of an internal crack. So here A is the length of the surface crack or half the length of an internal crack. So for a relatively long micro crack that has small tip radius of curvature, the factor A by rho t the whole raised to 1 by 2 will be very large, and this will yield the value of sigma m, that is many times the value of sigma 0. So if the micro crack has the small tip radius of curvature, then this value A by rho t the whole raised to 1 by 2 will be large and will be yield to sigma m, many times the value of sigma 0. So sometimes the ratio sigma m by sigma 0 is denoted as the stress concentration factor Kt. So Kt will be sometimes it will be equal to ratio of sigma m by sigma 0. So Kt is equal to sigma m by sigma 0, which is equal to 2 into A by rho t the whole raised to 1 by 2.